Hi, I'm Kewen from UC Berkeley. Today I'm very happy to present our paper, An Improved Sketching Bound for Added Distance. This is a joint work with Jing from MIT and Jelani Nelson from UC Berkeley. Let's first define what is an added distance. Assume we have two strings, x and y, and the added distance between x and y is the minimum number of insertion, deletion, and substitution operations that we need to get y from x. For example, if the first string is 01001 and the second string is 10011, then you need two edits. For example, you can remove the first character and add the last character. On the other hand, if here are your two strings, then you only need one substitution. Here is our problem setting. We have several clients and one server. Each client holds one file, and their goal is to find out which two files are the most similar ones. So they will compute sketch and send to the server, and the server will compute out the answer based on their sketch. For example, if you use platform like GitHub and Overleaf, then the file could be your code. On the other hand, if the file is an DNA sequence, then the server can be a giant database. Let's be more formal. Assume we have three parties, Alice and Bob and the referee. They share some public randomness. Alice will get a string x of length n and computes a sketch of length m. Similarly for Bob, he will get a string y of length n and also compute a sketch of length m. In addition, we are guaranteed that the added distance between x and y is at most k. And then the referee will get the sketch and needs to compute the added distance exactly with high probability. For this problem, a previous work by Blazowi and Zhang in 2016 showed that you can set m to be roughly k to the 8th times log n to the 5th for constant delta. And the folklore lower bound shows that you cannot get m to be sublinear in k. And our work improves previous bound to k cubed times log n cubed. As a remark, all computations in our algorithms are efficient, and the referee can recover added sequence in addition to the added distance itself. On the other hand, referee can report error when the added distance violates the constraint. Now let's turn to our algorithm. First, note that the added distance can be visualized by a matching. For example, the red singletons are deletions, the gray singletons are insertions, and the blue edges are substitutions, and the rest are the black edges which connects unchanged characters. Classically, we have the following dynamic programming, where Fij is the added distance between the first I characters of x and the first j characters of y. So by case analysis of the last character, xi and yj, we have the recursion. Coming back to our goal, let M be some optimal matching, then we can still run dynamic programming given the following partial information. First, we are given some black edges in this optimal matching, and then for other characters, we will reveal their value. We will try to reveal this partial information to the referee using a random walk technique from a result by Chakraborty, Goldenberg, and Kuski in 2016. Here we describe their random walk embedding. Let x and y be two strings, and we have randomness tape R. Then we will run embedding on x and embedding on y separately. Assume we are doing the embedding on string s, and first we append s with infinitely many zeros, and we initialize a pointer p, which starts from 1. For each round from 1 to 3n, we first output the character that the pointer points to, and then update the pointer by the value of the randomness tape, which decides whether to stay or advance. This means if we point to the same character, then the pointer will make the same move, which is a stable situation. On the other hand, if the pointers on x and y points to different character, then it will incur a random move, which is an unstable situation. Here is a concrete example. Assume x is 0, 1, 1, 0, and y is 1, 1, 0, 0. And here is the randomness tape. We will show how to embed x and y simultaneously. First, we initialize the pointer red and blue to the first character, and we output 0 and 1 because that's the characters they point to. And then, by looking at the first part of the randomness, we notice that it tells us 0 will stay and 1 will advance. So the blue pointer moves forward and the red pointer stays. And then output 0, 1. And from the randomness, 1, 0, we know that character 0 will advance and character 1 will stay. So only the pointer red will move forward. And then we will output 1, 1. And seeing the randomness 1, 1, we know both the pointers must advance. And to continue the process, we will output 0, 0, 1, 1, 1, 0, 0, 0 for embedding of x, and 1, 1, 1 with trailing 0 for embedding of y. Here are some properties of this random walk. First of all, the random walk goes through the whole string of x and y with high probability. This is because the marginal distribution on x and y is always half stay and half advance. Then we can show this claim by chain of bound and union bound. The second property is that if the random walk goes through S, then we can reconstruct S from the length of S, the random tape, and the embedding output. This is because we can reverse the walk by inspecting the random tape and also the embedding output. Here is the key property. We will show that the Hamming distance between the embedded output is at most 100k squared with constant probability. Consider a simple case where the string y is derived from x from one insertion, and let I and j be the pointers on x and y respectively. Then we will notice that I and j keeps to be equal until the insertion happens. And after the insertion, if we are in the situation of j equals I plus 1, then the pointers will synchronize until the end. Now consider a more general case, where y is derived from x by k insertions. Then, when j is between the t's and t plus 1's insertion, and also j equals I plus t, then the pointers will synchronize until the next insertion. Therefore, if we set delta to be I minus j, then delta can only be changed when the Hamming error occurs in the embedding output. And we will call this Hamming error as progress step. And when it happens, delta will have the following transition, which is actually a random walk. Since y is derived from x by k insertions, we know that the Hamming distance equals the number of progress steps to final synchronization, which equals the number of steps from 0 to k in a one-dimensional self-looped random walk. Therefore, from probability theory, we know that this quantity is larger than 50k squared with probability at most 1/6. For general string x and y, let z be an intermediate string such that both x and y can be derived from z by at most k insertions. And then we can use triangle inequality to prove our goal. Now, why is this helpful to our dynamic programming? We view the pointers ij as a moving edge on x and y. Therefore, the t-bit of the embedding gives Hamming error if and only if the it's character of x disagrees with the jt's character of y. When this occurs, we will review the characters. Therefore, the Hamming error is equivalent to progress steps, which means we will review values. And if we have no Hamming error, then it means we get an equivalent class. Here is our general framework. Let lambda be our CGK random walk on x and y. we will provide a sketch S for lambda. If xi equals yj, then the referee knows xi equals yj. And for xi disagrees with yj, the referee will know their real value. Here is the theorem of the construction. If the Hamming error of lambda is at most h, then S can be constructed of length at most roughly h. This uses a sparse recovery sketch to identify the difference in the embedding, and also use a full binary tree for the correspondence between the embedding and the original string. And for example, h will be roughly k squared with constant probability, as we showed in previous slides. Now let M be the black edges in a smallest optimal matching of x and y. Then we will generate several independent CGK random walks, lambda 1 up to lambda rho, to make sure that for each UV not in these black edges, there exists some random walk that will miss it. And this implies if we take the intersection of this random walk, it will provide black edges to be a subset of M. And also the characters outside this intersection will be revealed. And this means the dynamic programming will give the right answer. As for the final sketch length M, we note that M is roughly rho times H. Here rho is number of independent CGK random walks we take, and H is the number of Hamming errors we need to correct for each walk. The previous work by Blaswy and Zhang shows that we can set rho to be k squared and H to be k to the 6. And combined, they show that M is roughly k to the 8th. And we improve their results by a more involved and detailed analysis, which shows rho can be set to be roughly k and H can be set roughly k squared. And this gives our results k cubed. Furthermore, from CGK embedding, we know that H should be at least k squared, and we also gave an explicit construction showing that rho cannot be lower than square root k. In conclusion, we get an improved upper bound of roughly k cubed, and our approach is hard to get below k cubed and also impossible to get below k to the 2.5. And we know that there is a linear lower bound, and we and also the previous papers conjecture the lower bound can be strengthened to k squared. And there are many meaningful variants of this problem. For example, if we only output the distance, not necessarily the edit sequence, and even if we allow a constant approximation or polylogin approximation, can we do better? And in different communication setting, in one-way or standard two-way or bounded rounds. And for a different edit distance measure, for example, if we remove substitution, we will get LCS. And if we are only looking at permutation, then we get Ulam distance. For them, can we do better? Thanks for watching, and here are the references. If you have any question, feel free to ask me during the online session or send me an email.